Hi, and welcome back to our lecture series on computational finance. In this video, we'll start our discussion of the first actual topic of numerical analysis, and that is the numerical solution of linear systems and systems of linear equations, to be precise, which we will need in the process of portfolio optimization and actually in many other instances in applied finance. So this is the topic for this video. We'll start by first describing actually what a system of linear equations is. Now, in economics and finance, we often need to solve for these systems of linear equations. For example, it could be a production program. We have a certain budget, we have certain resources, we have a profit function, we want to maximize the profit function, and the constraints are a system of linear equations, for example. We write this system of linear equation in a standardized way. So this is what it looks like. We say we have coefficients a11, a12 to a1n, and we have our variables of interest, that it's x1, x2 to xn, and this has to equal b1. Now, this is the first equation, and because it's a system of linear equations, we have more of these equations. So a21, a22, a2n, and b2, those are the coefficients that are used in the second equation. Why are they linear? Well, you can see that we don't have any powers, we don't have any nonlinear expressions or functions in this equation, so this is a linear or an affine linear equation. And as you can see, we have n variables and m equations. So in form of a matrix, and writing this using matrices and vectors, the standardized form of a system of linear equations is given by A, the coefficient matrix, times the solution vector x has to equal the vector B. This is what it looks like, and we need to solve for it. Now, you probably have seen certain algorithms, methods to solve for such a system of linear equations in high school. Usually very simple ones where you only have 2 or 3 variables and 2 or 3 equations. Now, we want to do this on a much larger scale. So we also need methods that can do this numerically. We can do this in a much higher speed. And of course, if we have more coefficients, larger matrices, we also need to assess the accuracy of our solution. And for this, we'll later on look at the condition number. So we have already seen, actually, in one of our first examples, an iterative method to do this. What is an iterative method? Well, the methods you've learned at high school usually solve for the solution of the system of linear equations directly. So if you get the solution, it's usually the true one and the exact solution. An iterative procedure starts with a starting value or a starting solution vector, and then uses steps or iterations to improve on that initial solution in every step. And at some point, you stop. Now, we need to assess the quality, the accuracy of any solution, of our final solution, of course, but also in an iterative procedure of the solutions in between, in step 2, step 3, etc. For this, we first look at so-called matrix norms, and we look into the condition number of such a problem. So let's repeat something from one of the very first videos, actually, what the condition number sigma is. Now, we have a problem, f. We need to find this function f. We have a true starting value x. We have a disturbed starting value x bar. And of course, we also have a disturbed solution f using disturbed initial value. So that would be fx bar. The condition number here is defined as the norm of f of x, so that's the true solution if we are using the true input data, minus what would come out if the algorithm gives us the correct answer, but we're using wrong input data. So actually it's what happens if garbage goes in. The difference and the norm this gives us if we have an error, and if by accident actually we've gotten the correct answer, even though we've used disturbed erroneous data, divided by the norm of the true solution using the true data, input data. And this has to be smaller or equal than sigma times the norm of x minus x bar. That's the disturbance in the input data, divided by x, the norm of x. So on the right hand side, what we can see is this is actually the relative error in the input data scaled by the condition number sigma, and this has to be larger or equal than the relative error that we get if we put in erroneous data, false data into an algorithm that otherwise works perfectly. So we have no error coming from the algorithm itself, but actually we get an error because the algorithm, the method works fine, but we have errors in the input data. And the condition number in this inequation, it gives us a boundary, it gives us a bound on how much the initial error, the relative error in the input data, is scaled up or down by the algorithm itself. So this is the condition number. It tells us how much worse does it get if we have erroneous input data, and how much more does the algorithm add to this initial data error. Now, we've seen this with real numbers. For real number, you can just take the absolute value of that number, but for vectors and matrices, we need additional norms. We need a vector norm and we need a matrix norm. So for a real vector x, a vector norm is just a function that has the following characteristics. So it is always larger than 0 for every vector that is not the 0 vector. If we multiply it with a scalar constant c, the norm is not affected. So if you have a vector and you double it in size, it's just the double. The norm is just the double of that length, basically. And we have a triangular inequation, which means that if you have a vector x and y, it is always a shorter way to go directly from x to y other than going in a triangle. So the norm of x to y, the direct combination, is always smaller or equal than the norm of first going to x, the length of x, and then going to y. That's the triangular inequation. And if you're studying mathematics, you know this well. This is just the normal properties. These are normal properties of norms, now in the case of a vector. Some examples, for example, famous are the LP norms. They are defined as the P norm, LP norm of x, is given by the sum of all the entries in the vector, absolute values taken to the power of p, and then you take the pth square root of this. And if you now substitute p by, for example, 1, you get the L1 norm, which is just the sum of all the absolute vector entries. The L2 norm is also called the Euclidean norm. This is frequently used in regression analysis. This is the square root of the sum of squared absolute vector entries. And if you take the norm of a difference between the true and the approximate value, you can see this is basically the error term from regression analysis. And the L infinity norm, which is the maximum of the absolute vector entries. All three fulfill the properties we need for a vector norm, and these are frequently used in mathematics and actually statistics as well. And some examples in MATLAB, we have a very simple vector, 2, 4, minus 1, and 3. If we now use the function norm of v, 1, it gives us the L1 norm, and v, 2 gives us the L2 norm, and if we write v, inf, gives us the infinity norm. Especially the infinity norm is quite simple. We've seen it's the maximum absolute vector entry, so obviously this is 4. And Later on, we'll usually use norms whenever we need a metric for the error of a method or an algorithm. So if we have the entries of the vector, which are interpreted, for example, as an approximation error, you can interpret the LP norms as well. So the L1 norm is just the sum of the absolute errors. L2 is the error square root sum, and the L infinity norm is just the maximum error. So this is very, very simple. This is for a vector. We now also need this for a matrix. Similar properties. The matrix norm, A matrix norm, is a function on the set of now symmetric matrices. It doesn't work for n times m matrices. It's defined on the n cross n space of real numbers and matrices. Into the real numbers, the matrix norm of A is larger than 0 for every non-zero matrix. If you again scale it with a real number, with a constant, then the norm is just scaled up. And another triangular equation, the norm of A plus B has to be smaller or equal than the norm of A plus the norm of B for any two matrices that we are looking at. Again, some examples for matrix norms. For example, in this case, we have the L infinity norm for a matrix A, which is given by the maximum of the absolute values and entries in the matrix A if we sum it up over the columns. If we do the same, not for columns, but the rows, we get the L1 norm. Then the equivalent of the L2 norm is, in this case, the Frobenius norm, which is, as you can see, you take all the entries in the matrix, you square all the entries, you sum them all up and take the square root. And finally, we have the L2 norm, which is also called the spectral norm. And here you take the square root of rho of A transpose times A. And in this case, rho of matrix B is the spectral radius, defined as the maximum absolute eigenvalue of this matrix. So this is the spectral norm. Later on, we'll need the definition of what is called a compatible norm, which just means that, of course, we now have a norm for a vector and we have a norm for a matrix. And sometimes a vector norm and a matrix norm need to be comparable. And we call a matrix and a vector norm compatible if the following applies. We have the norm of matrix A times vector X, and the norm is smaller or equal than the matrix norm of A times the vector norm of X. Then in this case here, these two are called compatible. Last, we look at the so-called condition number of a matrix. I already mentioned that the condition number usually for an algorithm or for a mathematical problem gives us an understanding of how errors in the input data are enlarged or are decreased by the algorithm itself. So we have a disturbance in the input data, and this disturbance becomes larger or smaller as we solve for our mathematical problem. Now here we are looking at a system of linear equations, simply A times X equals B, and we now disturb the coefficient vector B by the term delta B. So on the right-hand side in the next equation, you can see that we are looking not at B, but at B plus this disturbance delta B. And this should, of course, result in a solution X plus delta X. It would be just coincidence if we arrive at the true solution X, but we have to expect that the disturbance delta B leads to a disturbance in the solution vector X as well. So in this case, we have X plus delta X. And put differently, we have A times delta X equals delta B. And this can also be written as delta X. So the change in our output in the solution we are looking at is given by A inverted times delta B. And with compatible matrix and vector norms, we get the following after we do some transformations. The norm of delta X relative, divided by the norm of x is smaller or equal than the norm of a times the norm of the inverse of a times the relative disturbance in the coefficient vector b. That's the norm of delta b divided by the norm of the original vector b. As you can see here, this is basically what we've seen before as the condition number of a problem. We have a disturbance in the input data. In this case, this is the vector b. We are looking at the relative error, so we divide the norm of delta b by the norm of b. And on the left-hand side, we have the disturbance that results in the solution of the mathematical problem we are looking at and we are looking for. This is the vector x. As a result, the norm of a times the norm of the inverse of a, so actually this part here, this is what, well, scales the input data error, the relative one, up or down. So this is the condition number. We call this the condition number of the matrix A. And of course, it's not for any problem that is associated with matrix calculation, but this is the condition number of the matrix A in the special case that we are looking for the solution of a system of linear equations with this particular matrix A as the coefficient matrix. The higher the condition number, the more the solution of the system of linear equations is skewed by the disturbance of the vector B. So this is an example in MATLAB. We have a very simple matrix A, 1, 0.6, 0.3, 0.6, 0.3, 0.2, and so on. And the condition number here in this case is 29.9666. If we were to use a very simple 3 times 3 Hilbert matrix, which is 1, 0.5, 1/3, 1/2, 1/3, 1/4, etc., you can see the condition number of this second matrix B is much, much larger. And in one of the first videos, I showed you that the solution of a system of linear equations with a Hilbert matrix as the coefficient matrix is badly conditioned. And you should change the matrix if you have the opportunities to. So this shows you how to simply calculate the condition number of a matrix in MATLAB, very simple function, cont of A or B in this case. Now, enough for the matrix norms, vector norms. We now have the tools to study some concrete examples for direct and iterative methods to solve for a system of linear equations. And this will be done in the next video. So thanks for watching and see you next time.